Hi, good morning, good afternoon, and good evening, everybody. And today we'll discuss about the we left with few topics yesterday, and today we'll continue with that. So let's do a fragmentation lab now. Yeah, we did only the PCAP, and we learned about the parameters of fragmentation yesterday, and today we'll do a lab. Let me share my screen for it. So let me quickly configure the IPs. We'll just do a direct connect, and there's a problem with the Wireshark with the other computer. So I had to change this. So if you look at this is the IP, the IP connection I'm going to establish between the devices. So I'm on R1. So this is the subnet I'm going to use for direct connect between R1 and R2. So I'm going to use 10.0.0 subnet. In the meantime, I forgot one thing. I will mute everyone. So I'm going to establish a connection to R2. So I'm on Ethernet 0/1 and it goes to Ethernet 0/0 on R2. So I'm going to configure it with an IP address there. IP address 10.0.0.1 on one end. So interface Ethernet 0/0, IP address 10.0.0.2/24 255.255.255.0. Let me try to ping the directly connected device, the R1. I can ping. So let me change the MTU on this. Let me take a quickly this. One second. I'm just fixing something here. Okay, so let me configure the MTU here, right over here. Change this. So let me take an MTU of 1200. Same 1200 over here. I'm going to interface Ethernet 0/0. IP MTU. I'm making it as 1200. Show run interface Ethernet 0/0. So the MTU is 1200 here. I'm going to R1. I'm going to do a capture here. I'm going to the R2 and I'm going to capture on Ethernet 0/0 to see actually the fragmentation is happening on the destination. So I'm on R1 now. Let me try to ping. I want to see the traffic is going through the link. Let me add this as a column, identification number. I want to show you something about that. So somebody asked me a question yesterday. I mean, what is the IP ID related to the fragmentation? Let me stop this capture. So when you click on this, you can see two arrows in the Wireshark. It shows you the ping request and the ping reply back. So there's a first packet. The ping packet goes from the 10001, the source, to the destination 10002. And you can see the arrow mark which points to yours. I mean, this is going to forward direction and it is a backward direction, right? So if you see these two packets, so you will come to know that this forward arrow indicates that it's a ping request going out from the device from this source 10001, and the reply I got it from 10002. So how do you find this helps you to find latencies. If you actually see this particular packet exactly at 955 milliseconds. Let me take this epic pen to annotate something here. So this is the time taken, right? This is milliseconds. So it took 955 milliseconds to send this packet back, and you got a reply back in 396 milliseconds from 10002 to 10001. It's in reverse direction. And if you see the the identification number, it helps you to find the packets, right? It's like stamping your packet. So your first packet goes out with the identification number, all zeros, you can see. And this particular packet, it goes with 001. So this shows me that this is the first ICMP packet and this is the second ICMP packet. Ping request, I got a ping reply, and this is my second ping request. For the second ping request, I got a ping reply back from the destination. If you see, it keeps incrementing, right? 3, 4. So totally I sent 4 ICMP packets and I got 4 ICMP packets back. So I'm not missing any ICMP packets. So this helps locally inside the LAN to figure out, is it my any ICMP packets is being dropped in the middle or it's being blocked. So the identification number is something you can use it to troubleshoot when you are doing an ICMP, when you do a continuous pings, and you can see where exactly you are losing your packet. That gives you a more granular way of troubleshooting when you're doing with an ICMP related troubleshooting. It helps you for that. So that's different from the fragmentation. So when we are coming back to the fragmentation now. So since I said it's a directly connected, and we change this MTU here to 1250 here on R2 Ethernet 0/0. And now let's use extended ping. That's something we can use in the routers to test your connection. So for that, let me do a ping. The protocol is IP, right? And I'll tell you one more thing here. What's happening? So IP interface brief. Load unassign. Config interface. The net 0/1. So I'm going to this particular interface on R1, Ethernet 0/1. And if I give shutdown, manually admin down, Ethernet 0/1, and no IP address. Okay. So when you don't have an IP address on a box, it's a brand new box, or it can be because of some problem. Actually, this is something. So I haven't configured any IP address on this box. So this R1 doesn't have any IP, and there's no routing happening here. And when we try to do a ping, it says an unknown protocol. So it's something you can look at your devices as your device is actually doing any kind of routing. Is it any interfaces or up? Because it is telling that it's an unknown protocol for ping, because we are not doing any routing there. We're going to Ethernet 0/1. We're going to assign an IP address. IP address 10.0.0.1, 255, 255, 255.0. Oh, shit. IPR. Ping 10.0.0.2. Now I'm going to use an extended ping. Ping, the protocol is IP. Target IP is 10.0.0.2. I'm from R1. 10.0.0.2 is the IP address assigned on R2. The input count is default. Datagram size, I'm going to give 1800. Time in seconds, default. I want to use an extended commands. Yeah, yes. Ingress ping, no, I'm not doing ingress ping. Source address 10.0.0.1. Anyways, if you have a one IP address, it doesn't have any other option. Always it picks your source address as your leaving interface. IP address will be your source address in any time when it talks to the destination. So it depends. So here you got two interfaces here. So if you have a WAN connection to this box and you don't have a direct connection between the, how do you say, I mean, from R1, if you want to reach R3, then if you don't define any IP address, so it's going to define it's going to pick this Ethernet 0/0, since that's the only way it can reach R3. So when you're doing some kind of troubleshooting with traceroute or something, you should know how the device picks the source address. So by default, it picks a leaving interface and depends on the connection what you have. Inside your routing table, you have a route for 11 network, right? So and you have this directly connected interface Ethernet 0/0. So obviously it's going to pick this IP address, the range, this IP as a source to reach R3. But since this we got only one interface is up and running, even though if you don't define this, it's going to pick 10.0.0.1. Even when the packet forwarding is happening between devices, even from your firewall, your load balancer, it's uh, it's very important to understand that how it picks a source address. So I'm not using any DHCP values. I'm not using any QoS. I want to set the do not fragment bit in the IP header. Yes, I'm going to set that in my IP header. So I'm not going to validate the data. Everything is the default. Now let's see the PCAP, what we see there. Here it is actually stopped with 100%. So I have to start this again. And R2 going to the capture, I'm going to capture the traffic on Ethernet 0/0 because the traffic comes in on Ethernet 0/0 from Ethernet 0/1 on R1. Going back to R1, trying to do the same process again. 10.0.0.2 going to R2. Datagram size is 1800. Extended ping. Source interface, I'm not giving anything here. It's going to pick 10.0.0.1. DF bit is all default. Okay, I don't see any traffic there. I try to ping 10.0.0.2. I can see the ping packet, but when I do this, not happening. So let's do it in the reverse direction. Let's do from source. In 002, 1500. Everything is default. So let me stop this capture. So what's happening here? We are sending this 1500 bytes of data. Yeah. And if I click on this guy, Let me drag this up. It's a bit slow. Just bear with me. So you can see these two fragmented packets, and Wireshark will show you the with the dot right over there. So you can see the two packets are fragmented here. So the fragment count, it says 2, and we have sent 1500 bytes of data. It just fragmented to 1176 and 304. So it can't do it in one go because we set the MTU as 1200. So it has to do a fragmentation. So if you look at this, the fragmented packets over here, it's coming from 10002 to 10001. How do I confirm in the device? IP traffic load fragmentation. So here R1, I don't see any fragmented packets in R1. So there are 5 fragmented packets here. So who is doing a fragmentation? The fragmentation is done by the router 2, 10002. So this is something, it helps you when you do a packet capture, you have to look for this, the reassemble packets here. So here the reassembly happened here. 1, 2, 3, 4, 5. 5 times we see this reassembly, and we should see all the traffic, right? I mean, all your data payload. We have sent something about 1500 bytes of data, and I should receive all the 1500 bytes of data. So that's how you should understand your fragmentation. If there is some fragmentation is happening and we are troubleshooting something with that, and you have to look for all these options. And let me show you one more use case. So if you look at this, this is some kind of a UDP traffic sense. And if you click on this, you can see a dot right over there. When you follow this dots, 1, 2, 3, 4. So this is all fragmented packets. You can find it there. And your payload here, it's totally, they have sent 5387 bytes of data, and it's been fragmented into 4 pieces, and it reassembles. This is one common UDP traffic that goes, but UDP is an upper layer protocol in the OSI. When it pushes down to the lower layer protocol, layer 3, it can't, it cannot push the 5387 bytes of data in one go, so it fragments the data. So this is how it works with multiple protocols. You can find if the fragmentation, if you see some, if you're doing some packet analysis, you can figure out, is it the number of packets, the payload, whatever I have sent, is it properly being delivered successfully there? Right over here, you can see all your fragmented packets. As I said, if you calculate, you will get the whole data what you have sent. And also you can make use of this field. I generally use this, the length field here. It gives you the number of payload. 5379. So you can go to the corner of this capture and you can see the length of the packet. So and if you see this particular packet, what we are looking at here, the option to mark the packet. So now I mark this particular packet, right? If you go right click and do a marking, it marks with blue color there. So if you calculate this data, 5379 bytes of data, you see right over here, from here, it's been fragmented and reassembled right over here. And you get all the data, the payload that's been fragmented. So yeah, this is a use case for the fragmentation. So when you do troubleshooting, when there is some fragmentation issues, and if you're missing out some data, maybe right. I mean, if the device is not capable of doing a proper fragmentation, and if your MTU value is too low, you can go ahead and tell them why this particular device has an MTU got a very less MTU for it. Is it any specific reason for it? So the data is being fragmented a lot, and I see a latency. So I have seen some such problems with the fragmentation. If the MTU is very less, somewhere around 1100 and 1200, you might experience a problem when you're pushing a large amount of data. So that's a takeaway of this fragmentation lab. Let me put up this. So next, let's jump into the topics we have. We did this PMTU. So now we are going to do some different TTL scenarios here. So TTL has, as I said, the TTL should always have a value. Let me open up a PowerPoint very quickly. Here's my PowerPoint. So far, we covered, I mean, the version we know, we are using IP version 4, and the total length of the packet we have seen. And I'll show you the fragment offset there. Source address, destination address, and IP option is something we are going to do now. And the one more important field I said for troubleshooting is your TTL. And identification. Identification number, I have shown you how do you find your IP identification. So we covered the most important IP header parameters. I mean, what should we look and concentrate when we are troubleshooting your IP header parameters? So now let me show you what is a fragment offset. So here, if you see this, the flags, you see that there is a fragmentation. Whenever you see this particular flag in right over in your IP v4 header, So right below that, if you see this fragmentation flag set, so if it is all zeros, right? If you go for anything with zeros, so here if you see zeros, right? So there is no fragmentation happening here. But if I go here, there is a fragmentation happening. Where? In 10002, not in 10001. So from this fragment flags, you can figure out who is doing fragmentation. So here 10001 is not doing a fragmentation. So 10002 is doing a fragmentation because it sets this value. If you see the source IP address here, it is 10002. So each sets a fragmentation because that guy is doing a fragmentation because it doesn't have an default MTU. We just purposely we reduce the MTU size. So he is doing a fragmentation. So all these fields are helpful when you troubleshoot, when you're doing when you're analyzing a package, when you look through your eyes, you should look at all these options, the very important options, what we discussed here. You have to look for your TTL, you have to look for your fragmentation flags. So this is called a offset, fragment offset values. So we are sending a data here, right? So we send a data of 1480 bytes of data. The fragment offset starts with 02175, frame 18. Yeah. If you look at this, this is the fragment offset values, it's 18. So out of 1500 bytes of data, this offset carries 1176 bytes of data. And the second offset 19 carries 304. So this helps you to figure out if there is some packets missing in the middle. Say, for example, you have sent 1500 bytes of data, and if you don't see a frame set offset value, something is a 19 missing. And if you receive 1176, there could be some problem with the latency. There could be some problem with something else. But why we are missing it? That's something we can look when you do a capture, and you can figure out, and you can do your troubleshooting where you can look for either this particular device CPU spike too high, and because of that it can't do the fragmentation, or because of the latency it can't do a fragmentation. But the whole point is, when you are analyzing the packets, do you see all these packets has been properly arrived to the destination? So that's really about the fragmentation. Now let's jump into the different type of TTL. So as I said, let me open my PowerPoint. So we discussed about the frame fragment offset, IP flags, identification, TTL. So now we are going back to the TTL again. So when we talk about TTL, there are two protocols being used for TTL. One is UDP based and TCP based. And the values 64, 128, and 255. I think Cisco uses an UDP. We'll do a testing now. And some Linux boxes, they also use a UDP. So whenever there is a routing, TTL is very, very important when you do from any irrespective of your firewall, load balancer, or routers, switches. If a device is capable of doing a routing, and if you expect a device to reach, example, I can reach a network 192.168.0.1. It can be anything in an example, and it comes with the source traffic 10.0.0.2. So 1, 2, 3, 4. So it is 4 hops away. So the TTL it takes is 4. So if you calculate this, if I do a ping for 192.168.0.1, my TTL should be 4. So what should the TTL value is? I should see in the Wireshark, it should be 60. So it means that there is 4 hops away and my packet is routed properly. But if you see something like maybe 58, but actually there is only 4 hops away, So now it takes 6 hops away. That's not expected. That's something you should focus on your troubleshooting with the routing in the middle. It can be any device, as I said, but TTL is very important to understand. Even I had a scenario where we had a routing problem with Microsoft Teams. So generally, it's a device. They are using an application here. It's a Teams application using here, and there is something this you know the 52 subnet is used for your Teams traffic. It can be anything. In my scenario, I'm telling it's 52 is the subnet used for Microsoft Teams traffic. The user traffic should be authenticated. But for some reason, this routers are receiving this 52 subnet from a different devices, from a different routers. But it is something it should go direct internet out from the said end device. But it was receiving this prefixes from somewhere else. And this Teams users are redirected back to that particular boxes and the TTL is too high. Example, it takes 15 hops, but actually it should be the TTL should be 10 hops. So just with TTL, you can figure out, okay, why this traffic is taking 15 hops away. It should be just a 10 hops from my source to the destination. Why it should take 15 hops? It's been redirected somewhere. It's been taking a very longest path. That's not expected. That's something that's the whole point I am telling you. I mean, how you understand your TTL, that helps you for your troubleshooting. There is no one-stop solution for finding all your problems, but how good are you with the protocols, what you understand, and when you apply it with your, your real life, then yeah, you will definitely get, good results, and you can troubleshoot better. So now, when we're coming back to the TTL testing, let's go back here. Let's see what kind of protocol this particular device is using. I think Cisco is Linux based, and most of the devices are Linux based. I think they mostly use UDP based. I haven't tried with other boxes. So for this TTL, I want to increase this TTL value. So I want to bring up this loopback interface. And also these two. I mean, we are going to spin up, I mean, not spin up, I mean, we are going to enable the IPs on these interfaces, and let's do a testing again. Because I want to see some TTL decrementing here. So, and also we should see what kind of protocol is used for that particular TTL. So since this is an IP communication, let me do it very quickly. So I'm going to configure this interface Ethernet 0/1, which goes to router 5. Interface Ethernet 0/1, IP address 13001. We are using an universal subnet /24. And also here also we'll change the TTL, and let's see this time what happens. And along with that, I mean, along with this TTL, we will also do this fragmentation testing on this particular interface on R2 Ethernet 0/1. I'm going to go ahead and change my IP MTU 1200 interface loopback. Sorry, yep, interface loopback 0. Going to assign an IP address. Since this is a router 2, I'm going to use an IP address 2.2.2 or 255. Going to R5. Host name R5. Interface Ethernet 0/0. IP address 13.0.0.2. 255, 255, 2550. No shit. So to exchange the routes, I'm going to use an OSPF. As I said, you can do any kind of routing protocol you want. This is not specific to that. Just it's a very simple way of advertising my network. So I'm going to do that. Fake router OSPF1. You can do router OSPF1 if you're doing the same lab. You can enable OSPF on all the interfaces. That's the meaning of this, all zeros, area 0. Going back to R2, network all zeros. Going to R5, route OSPF1, network all zeros, area 0. Okay, from this guy, if I do trace route to 10.0.0, sorry, 13.0.2, wrong IP address, 13.0.0.2. Do you guys know that what is the maximum hop count for a routing? So the maximum hops is 30 hops. That's usually I have seen in many scenarios. It can't be if your packet is going beyond 30 hops, that's not routable. We go back to R5 and I try to show IP route. What do we see there? Can I ping 13001? Can I ping 2.2.2? So I'm trying to ping from R5, I'm trying to ping this loop back 2.2.2. It's on R2, but I can't. I do ping 2.2.2. So neighbor 13002, it's a dropping the connection. So if I go to, I think it's because of bad MTU. Let me check. Doesn't like an MTU. Let me try. Yeah, because of an MTU problem, I think. Yeah, I think the same thing happening between these two boxes there. So what if I try to ping this guy from ping? I'm on R5, I'm trying to ping 10001. It's on router 1. I can't. Wipe it off. I can see 10 network. I can reach 10 network through 13. I think it's again because of a bad MTU here. Let me try. It's 13 is flapping and also the 10 is flapping here from R2. Show run interface Ethernet 0/0 config face Ethernet 0/0. No IP MTU 1200. Going to R5. I can ping now. So you can see this. So if there is a different MTU on both directly connected devices, OSPF doesn't like it. So that's MTU is very important when you do troubleshooting with your networks. So let me try to do a trace route now. Let me do a trace route to 13,002. 13,002. And okay, I want to try this option. If I do with a TTL of 1, minimum and maximum 1. Let me take a capture on this R1, go to capture. The living interface is Ethernet 0/1. So when you're doing a capture, you have to do only for the IP address, the destination IP, 13,001, sorry, 13,002. So, so that way you can filter the traffic only for the team. So the TTL what we have given, it's a TTL is 1, 10,001, 30,002. So your first packet goes from, what is that? When you do it from for 13,002, I get a reply, this guy, right? 10,002 is sending a reply back to 10,001. Time to leave exceeded. It makes your TTL 0. So again, this guy is sending a TTL, right? Because we made it purposely, we made a TTL value of 1. We made it to 13,002 and 10,002 is decrementing it. So I think my packet is not forwarding. So the TTL of 1, I can reach only one hop. It decrements the value, make it 0, and I can't, the packet is not moving forward. What if I don't define the TTL? And if you see this, this is an UDP based. And let's take in Windows, let's see what kind of protocol it's using. It should be in TCP or UDP based. So now if you see the TTL has been incremented to 2. With the TTL value of 2, I can reach the destination, not with 1. If I make it to 1, you have seen the output. This is the output I get with the TTL of 1. So we are not controlling anything with the TTL. What we are telling to this box is, can you reach this box with one hop? It is telling, no, I can't. With one hop, I can reach only 10,002. And what are the other things you have to look into your TTL? See, for this is a this is a Wireshark and this is a simulation tool. So generally, if it is a one hop, maximum it would take 1 or 2 milliseconds. So in an average, right, this is an average. The middle one is the average. This is the longest time it takes. The minimum, maximum value, but the average you have to look always for the middle value. That's the middle value is your average. So if it is just one hop, you should not see more than 1 millisecond. Then it is a slowness problem. See, if you look at this is the first packet. When I send from source to destination 10001 to destination 13002. So apparently 10002 should send a reply back, right? You guys got the TTL. See, when I make a TTL of 1, I send the packet to R2. It makes the TTL 0 and sends a destination unreachable message to R1. This guy makes a TTL of 2. So it goes here. The TTL becomes 0, goes back here. Then again, since it made us a TTL2, now it can go for 2 hops. So in every hop, that's how it tries to find the number of hops. So I have to go 2 hops to reach this particular destination. That's the whole meaning of it. And with the captures, what are the key, tiny details you have to look for when you're troubleshooting? It's the slowness here. So the time taken for this guy, 10002 to 10001, it takes 4 to 22 milliseconds. And if you look at this particular packet, what is this? It takes 114 seconds, 100 seconds. It's somewhere around 2 minutes. This is definitely this is not good. And then the production, you shouldn't see something like this. It takes 9 milliseconds. If you see there is in the middle, there is a spike. That's because of the tool is doing that. But when you see the real-time trace routes, you should not see the latency like this. It's just a direct connect. It should not take 10 seconds for it. And how you should calculate your TTLC from here 10001, now it is talking to 13002. If you go back to the last packet, if you look at here, the traffic is between 10002 and 10001. But the finally 10001 is making to 13002 and your TTL is 2. That's your actual TTL value when you reach your destination. Let me check is that I have any TTL related. Okay. So now let's do TTL in the Windows machine. If you see my total hops is 10 hops and all you can see the values here, right? In an average, it is not taking more than 10 seconds here. Everything is below 10 seconds. That's a good connection here. But if you see somewhere around, I have seen in some situations with this trace route, you can figure out your slowness. Which particular hop has the highest value? That's a culprit there. I mean, there is a problem with that particular box. In mostly in the ISP, I would suggest you should ask them for the BGP flapping or some kind of it is doing some kind of very intense task in the box. Okay, now let's do a capture for this. Uh, Let me spin up this Wireshark. I'm interested for here. Let me bring up this here. I'm interested in the traffic 8.8.8. Let me do a trace route back again. The wrong Wireshark. Yeah, this is a file. Yeah. I think still the trace route is going on. So with the trace route, what you should say when you're doing a capture, so it is making to the first hop 192.168.0.135. This is my PC, right? 192.168.0.1. It sends 4 ICMP packets. And if you look at this, I got a reply back from this 10 to 32.0.1. That's my first hop, right? This is my 192.168.0.1. You can compare with your trace route outputs, you will understand. So side by side. So 10.232.0.1, it's sending a reply back to this guy. So I reach first hop. So I have got a routing. And they are blocking this ICMP in the middle. And this is going to 49.205.72.39. And then finally, if I drop down, so here 8.8.8 is sending a reply back to me. And what is my TTL? So it started with TTL, it shows us 58 here. So what is the protocol used here? I think this should be using a TCP. Got freezed. So I'm telling do a capture for TCP traffic and IP address is 8.8.8. Let me try with UDP. Let me research on this and come back to you. I think it should be a TCP or UDP, but I don't see any kind of specific protocols being used here. So that's how you will calculate your TTL, and I think here it is using 64. There in the where is it in the lab Cisco box is using 255. That's a TTL 255 here. So on 128 in some scenarios it uses 128. So your the most I have seen the values used in TTL are 128, 255, and 64. So now finally we'll do the ICMP labs today. Then followed by that we will do a spoofing lab next week. So let me open up this. Helps you to understand ICMP related troubleshooting. We'll do. One minute. Let me open this. Okay. So what we are going to look today, I mean, not we are going through all this ICMP codes. The very important and most widely used for troubleshooting is something we are going to discuss. So one of the most useful ICMP codes is something we should know about the host and reachable. So this is a destination unreachable, and it should return with the code 3. So let's do that ICMP testing, and we'll figure out. We'll go one by one. So I mean, we got different types of ICMP codes. For echo reply, it should be 0. It is the destination unreachable is 3. So we are going to try with echo reply and destination unreachable, and how you will troubleshoot with that. I'll walk you through the steps. So this is, if you see this code 0, right? So let me go back. So code 0 stands for echo reply. So you get an echo reply back for code 0. So if you see this echo ping reply, so if you want to see only for the ICMP, I think it's very generic. You guys will be using it. You can type in only ICMP, will show you only the ICMP messages. Okay, so now we'll do the testing for ICMP destination unreachable code 3. So for that, let me on this. Let me stop all the captures. Start it again. So I got a route for 10002. So let me try to ping an IP address, which is not in my routing table, and let's see what is the response I get. Capture Ethernet 0/1. Going back to R1, keep it in the top. So let me try to do, I don't know where is 3. Let me do a trace route 3.3.3. Okay, so we'll close this connection. So let me go to R5. So if I do show IPR, so I see 13001 and 13002. Let me try to ping 13005. So let me stop this. Let me just type R packets here. So I got a routing table, can be any layer 3 box. So I got a routing table here. Oh, IP route. So I got a routing table and it costs, it knows how to reach this 30 network because that is directly connected. But I am trying to reach an IP address which is not actually connected in this particular network, right? So all I see for the 13 network is 13.0.0.1, 13.0.0.2, and 13.0.0.5. So my packet will be only forwarded if I know the destination MAC address of it. So it is trying to do a broadcast. Yeah, we discussed this before, the ARP. It's an ARP request. For this ARP request, nobody is sending a reply back. So who is 13.0.0.2 here? This guy. It is asking the gateway, do you know how to reach this 13.0.0.5? Right? Because I couldn't find it locally. Because I did a broadcast. Broadcast is local to the subnet. I did a broadcast, but I didn't get a reply back. So if your ICMP packets has to be, when the ICMP packets has to be, what do you say? Without your ARP request, your ICMP packets will never leave, or your ICMP process will never kick in. I would say, precisely if I want to say, if your ARP response, if you don't get an ARP response, you don't see your ARP reply back. If you don't see your ARP reply back, you don't see your ICMP. So your ARP is a base connection for your ICMP. It can be for anything. Correct. And don't confuse with the retransmission and ARP. Some people, they do that. Retransmission is only for TCP. When you completely deal with the troubleshooting, when it comes to the layer 2 and layer 3, all you deal with ICMPs ARP. So in the ARP, I didn't get a reply back. So I don't see any kind of ICMP packets here. So now let's do a simple testing with this. Let me go to our, I'm going to block this ICMP packets here and let's see what is the response we get there. So I'm going to Ethernet 0/1 on R2. Interface Ethernet 0/1. Interface Ethernet 0/1. IP access group. I'm going to just block this purposely to see the ICMP codes. I'm going to say I'm going to say this access group as ICMP. So the traffic is coming inbound from R5 to R2, the traffic coming in, that is an inbound traffic from R5 to R2. So I'm going to block this inbound. IP access list extended. I'm going to use the same name. It has to be same name, the access group and your access list. Deny ICMP any kind of ICMP traffic, deny. I'm doing it in R2 and I just logged into the R5 now. Then let me try to ping. I want to ping 13.0.0.1. If I do a Wireshark, I have to change some value here. I'll tell you how to do that. It's filling up the buffer very quickly in Wireshark. capture, it's a Ethernet 0/1. Okay, capture Ethernet 0/1. So when somebody is doing this, even in your firewall, but how do we check that I have a route for this guy? I give show IPR. I can see the destination MAC address. This guy, this is that I know this 13001 is my R2 in the middle, 13001, but it is telling that destination unreachable. But one more thing, it is highlighting that the communication is administratively filtered. So they are blocking it. So I don't see a response. So it doesn't mean that I don't have a connection. I have a connection, but they block the ICMP. Even in the firewall, if you try to ping, you guys will have encountered this problem. They block an ICMP and you can see this communication administratively filtered or something. If you want to probe that this is not actually the devices, the destination is not reachable, it is because of a rule or policy is blocking this, but your actual routing is happening. So this is the proof where you can find it. So if you go to this ICMP packets, so this is code 3, destination unreachable. And on top of that, you get a clue that communication administratively filtered. But I think if you go to the actual box, if you do a debug IPICMP packets all, what do you see for it when you do that? So you have a routing, you're sending a full packet. The destination is this, source 13001, and destination is this guy, PC traffic. But we can't see anything related to the policy filtering, right? But here you can go, you can compare your destination codes, sorry, your type code, and along with that, you will see the communication administratively filtered. It means that the policy is blocking it, but you have a routing. And yeah, what else? But if it, I have shown you, if there is no route for a particular destination, you can't see your ICMP unless you get an ARP response back. So you might be continuously seeing your ARP request. And for your ARP request, as nobody is responding, so your destination is unreachable. That's different from this. That's a comparison when you have to do when you're troubleshooting. When you ping, you don't get your ARP response back in your capture. So it means that the actual destination doesn't exist. It's not connected to the network. But if you see something communication administratively filtered and code 3, you have a connection, you got a ARP response back. That's why your ARP table has completed your IP and your MAC address detail, but it's been filtered in the middle by any device. That's policy filtering. That's not related to the routing. That's how you can compare your test results and you can do your troubleshooting. Let me stop capture. Somebody sent a message. 255. Okay.